Hey everyone and welcome. If you've ever been deep in a Go project and felt that code complexity just starting to creep up on you, well, you are in exactly the right place. Today we're cracking open the developer's toolkit to talk about design patterns. Specifically, we're going to zero in on the creational patterns. These are the ones that help us create objects in a really clean, flexible, and efficient way. Let's get right into it.
So this is the big question, isn't it? It's the one we all face. As our apps get bigger and more features get added, how do we stop our code from turning into a giant, tangled ball of spaghetti? How do we build things that are not just functional, but also easy to maintain and for our teammates to actually understand? Well, the answer is, we don't have to reinvent the wheel.
And that, my friends, is where design patterns come to the rescue. Think of them like blueprints. They're not chunks of code you can just copy and paste. Not at all. Instead, they're proven, battle-tested templates for solving problems that pop up over and over again. It's like having the collective wisdom of thousands of developers who've already tackled the exact same challenges we're facing today.
Okay, all of these points are fantastic, but let me tell you, that shared vocabulary one, that is a total game changer. When you can walk up to a whiteboard and say, hey, let's use a builder pattern here, everyone on your team instantly gets what you mean. They understand the structure, the intent, the whole shebang. It's a professional shorthand that just speeds everything up and makes sure you're building on solid foundations.
Now, to make sense of all these patterns, we don't just throw them into one big pile. That would be chaos. They're actually neatly organized into 3 distinct families, and each one tackles a completely different aspect of software design.
And here they are. First up, you've got creational patterns, which, as the name suggests, are all about how objects are created, how they're born. Then you have structural patterns, which are about how we piece together objects and classes into larger, more useful structures. And finally, behavioral patterns, which are all about how objects talk to each other and divide up responsibilities. Today, our focus is going to be squarely on that first category, the creational patterns.
So let's zoom in. We're going to explore the very art of creating objects. This is about the very beginning of an object's life. These patterns give us incredible flexibility and control over how we instantiate things, which ultimately makes our systems way more dynamic and loosely coupled.
So you might be asking, why do we even need special patterns just to create an object? Well, it's because they solve some really nasty code smells. They prevent something called tight coupling, where your code gets hardwired to one specific class, making it a nightmare to change later. They also help us follow the single responsibility principle, the idea that a class should really only do one thing well. This way, a class can focus on its job without also having to worry about the messy business of creating other complex objects.
All right, our first pattern is the singleton, and this analogy just nails it. In some systems, you absolutely need one and only one instance of something to coordinate everything. Think about it.
At its very core, the Singleton pattern is all about guaranteeing that uniqueness. In the world of Go, a fantastic way to achieve this is with the sync.once type. It's perfect because it ensures a block of code runs exactly one time, no matter what. It's ideal for things like a system-wide logger or a database connection pool where you really don't want more than one. But, and this is the senior level take, you need to use the Singleton with extreme caution. Why? Because it introduces global state into your application. This makes unit testing incredibly difficult because you can't just swap in a mock or a fake version for your tests. This is why a lot of experienced engineers will actually prefer something like dependency injection over the Singleton. It's powerful, for sure, but it's a tool that can really burn you if you're not careful.
Next up, the builder pattern. I absolutely love this analogy. Building an object isn't always a simple one-step process, right? Sometimes it's more like building a custom sandwich. You've got a lot of choices to make along the way.
The builder pattern is designed for exactly that situation. Instead of some horribly long and messy constructor with 10 different arguments, the builder lets you specify what you want piece by piece. In the Go community, this is often done so elegantly using the functional options pattern. It gives you a super clean, readable, and extensible way to build your complex objects. The biggest win here, by far, is readability. The code you write to create an object almost reads like a plain English sentence. It also makes it super easy to create immutable objects, which is a massive plus for writing safe, concurrent code. The main downside? It does add a little bit of extra code, so it might be overkill for really simple objects.
Okay,
Let's switch gears and talk about the prototype pattern. This analogy from biology is just spot on. Sometimes the absolute best way to get a new object isn't to build it from the ground up, but to just clone one that you already have.
This pattern really shines when creating an object is an expensive operation. Just imagine that setting up an object requires a slow database query or some really heavy calculation. If you need another object that's almost identical, why would you do all that work again? With the prototype pattern, you just ask the original object, "Hey, can you make a copy of yourself?"
Now, the trade-off here is complexity. Since Go doesn't have a built-in clone feature like some other languages, you have to write that copy logic yourself. And this forces you to think about the tricky difference between a shallow copy, which can cause some weird unintended side effects, and a deep copy, which is much safer but also more complex to implement.
All right, on to our fourth pattern, the factory method. This logistics company analogy sets the stage perfectly. You've got this general idea, right? We need to transport something, but the specific vehicle you need depends entirely on the context.
The core idea here is one word: delegation. A parent type says that an object needs to be created, but it lets the child types decide which specific kind of object to create. So the road logistics type knows it needs to make a truck, while the sea logistics type knows it needs a ship. It's all about delegating that responsibility down the line.
The biggest benefit here is how it decouples your code and makes it extensible. Your main application code doesn't need to know anything about trucks or ships. It just cares about the general transport interface. This is a beautiful example of the open/closed principle. You can add new types like air logistics, creating an airplane, without ever having to change your existing working code. The only downside is you might end up with a lot of creator subclasses.
And that brings us to our final pattern today, the abstract factory. If the factory method is like a single factory, think of the abstract factory as a whole factory of factories. The IKEA analogy is perfect. It's not about creating just one product, it's about creating an entire family of related products that are all designed to go together.
The key idea here is all about ensuring compatibility. When you use a modern furniture factory, you're guaranteed to get a modern chair, a modern sofa, and a modern table. The pattern makes sure you won't accidentally get a Victorian chair that completely clashes with your modern sofa. It enforces a consistent theme across a whole set of objects.
This pattern is incredibly powerful for maintaining consistency, but its main drawback is rigidity. If you suddenly decide that every furniture family should also have a lamp, you have to go back and change the main abstract factory interface, and then you have to update every single one of your concrete factories to add that lamp. It's powerful, but man, it requires a lot of careful planning.
Okay, this is a question that comes up all the time, so let's just clear it up right now. The easiest way to remember the difference is to think about scope. You use the factory method when you need to create one single product from a list of options. You use the abstract factory when you need to create a whole family of related products that have to work together. It really boils down to a single object versus an entire product line.
And there you have it, our tour of the creational design patterns in Go. These are so much more than just clever solutions. They are a shared language, a language that lets us design and talk about software at a much higher, more abstract level. They give us the vocabulary to build systems that are more robust, more flexible, and way easier to maintain. So the real question is, now that you're starting to speak the language, what are you going to build with it?